Okay, we are recording. Good morning. I am just getting a handout ready here that I should have had posted already. So let's see here. Okay, there we go. And we'll get that posted over to D2L. Ah. Oh, I gotta get the quiz key up too. Let's see. Oh, we had Brittany and we lost Brittany. All right, I just posted kind of at the end of unit 4, sub 4.7 and 4.8 examples. Should put that in the chat. Actually, no, you can't see the chat until you join. Man, I do not like teaching online. Maybe if I was more prepared and like knew more in advance and had everything ready to go, it'd be better. I'm just gonna post on a news post here. Okay. Let's look at the schedule. Lots of windows open. That is not good. Okay. Well, I guess we don't need that one. All right, so as promised, I did post, I should get the chat up here. I did post a schedule, a plan. Oh, there's a few posts down here. So we are going to have an exam. We talked about this last time. We're going to have our next exam after class on Thursday. So today we're going to focus on homework questions and some examples from 4.7 and 4.8. Good morning, Juan, Tavante, Tyler's here, JT, Sandra, Christopher, Haley, Chantel, Brittany, and Albert. Excellent. It's a good turnout. Yeah, I guess, let me see here. I guess we'll start with homework questions. 2 sections, optimization, and then antiderivatives, which is going to be the foundation for the rest of chapter 5 and pretty much all of Calc 2 and Calc 3. For those that are headed there. So that's 4.8 is setting some foundation for that. Let me pull up a blank sheet here, and I was having trouble with the online textbook, so I actually had to download it from 4.8. So I have 4.8, and then I think 4.7. Oh, I closed the window, shoot. So let me get up 4.7. Let's start with homework questions. If anyone has any from the optimization in section 4.7. Anyone want to get us started? Get that up here. I don't have everyone. I don't see any hands raised or questions in the chat. Anyone have any optimization questions?
Can you go over 3?
Yeah, sure. Let's take a look here. Number 3. All right. Oh, we keep losing somebody. Coming in and out. Okay. So let me take a look here. That one over here. All right, find the dimensions of the rectangle with the largest area that can be enclosed on all sides by L meters of fencing. All right, now here is your question 2. We'll do that one next. What I always start with optimizations, I actually have in the examples that I just posted, so you don't have it yet. But let me just kind of highlight, this is what I have in my notes. And I know Dr. Sugar didn't have something exactly like this, but this is what I like to do. Essentially what you're trying to do is you're trying to create some function, some quantity you're trying to optimize, and then you do these first derivative equal to 0 to find those maximums. And so what I like to do is I like to draw a picture, label anything on it, and then state what it is you're trying to optimize. So let's do that for this example. It's a rectangle, okay, that's exciting. I'm going to label length and width. That's all we have. We don't know what those are, but obviously it's a rectangle, so those are going to be important. And then let's see, we want the largest area, so we want to maximize area, and of course area is length times width, and we have L meters of fencing. L meters of fencing. Well, that's perimeter. So L is equal to 2 times, this is a bad idea to do L twice, but whatever. Why did they use L? L meters of fencing. Maybe length, capital L for length, I don't know. Okay, so right now I have a function, but it is a multivariable function. It's a function of 2 variables. That's not good. You can actually solve this problem. My Calc 3 students just finished doing this a couple weeks ago. But in Calc 1, you need a function of 1 variable. This is called single variable calculus. So that's where you usually use the other fact you're given, in our case, using this, that we have capital L meters of fencing. So what I'm going to do is I'm going to solve, and you can solve for either the length or the width, either one. And I think I don't really want 2 different L's. So what I'm going to do, I'm going to choose just kind of arbitrarily, but I'm going to solve for L. That way I can get rid of it. So that'll be capital L, let's see, well, 2L minus equals capital L minus 2W. And so my length will be capital L minus 2W over 2. Keep in mind that this capital L is a constant. It is whatever, how much fence we have. A lot of times they do these with a given number, and it's almost easier then, but keep in mind that's not a variable, that's just a number. It represents a constant. Whereas the length and width are unknown variables. So now the reason why this is helpful, now when I put in and substitute in L minus 2W over 2 times W, now this is just a function of width. It's a little awkward the way it's written, so I'm going to do this. 1/2 times capital L minus 2W times W. I'm going to multiply that in. capital L over 2 minus W times W, and then get like a cleaner version that's capital L over 2 times W minus W squared.
I'm sorry, why is it times W, not plus W?
For the area, like that times W,
Oh, times.
right? For area. Yeah, it looks like plus, but it's just a messy penmanship there. But it's, yeah, length times width. So for most students, why is it also over 2? Could you specify it, Tyler? Why is it also over 2? What is it? Yeah, so if you think of when you have 2L equals capital L minus 2W, you divide both sides by 2. So you have to divide the entire right-hand side by 2, not just the 2W. You have to divide the whole right-hand side. Is that what you were asking? Yep, it's all good, no worries. Remember when we were doing related rates, we struggled, there's a few areas we struggled with there, but a lot of times we struggle just to get the equation. What is the equation? Optimization is the same thing. In principle, you know, my kind of the idea here is you want to find this maximum. So, hey, you just take the first derivative, set it equal to 0. That's, how hard is that? But in principle, the hardest, or in practice, when you're actually doing it, the hardest part is getting the equation. So now we have the equation, and again, keep in mind, capital L is not a variable. So when I take derivative here, there's no product rule. It's just a constant, like 20. So when I find the derivative a prime of W, that L over 2 is just a constant. And then the derivative with respect to W here, a is a function of W. So we're finding a prime of W, that'll be minus 2W. And we're going to find critical numbers. So we're going to set that equal to 0. Oops, sorry, jumped too far. So L over 2 will be equal to 2W. And then W will be capital L over 4. I don't want to solve for capital L. I'm trying to find the dimensions of the rectangle. So I'm trying to solve for length and width. So the width is whatever, how much fence you have is over 4. And then let's see here. What are we looking for? Find the dimensions. Find the dimensions. So we need the length also, but we know the length is capital L minus 2W all over 2. You know what? There's an easier way to do this. I'm going to go back to, maybe it's the same. That's all right. So we're just going to substitute in the W that we found. It's just a little tedious here. It's just basic algebra, but we get L minus L over 2 all over 2. I guess L minus L over 2, don't make that more complicated than it is. 1L minus half of an L is half of an L. And then half of an L over 2, half of half is a fourth. So in fact, they're the same. They're the same. So if you want to get an optimal square, however many feet you have or meters you have, you should just, if you want to make an optimal rectangle, the rectangle that is the largest is actually a square, where each side is a fourth of the length that you have. And so those are the dimensions, a fourth of that capital L. So Christopher, does that clarify your question? Do you have any additional questions on that one?
No, I'm fine. Thank you.
Yep, good one. Good one. Any other, I know Haley has a question about number 11, but any additional questions on number 3 before we move on to that one? Okay. While I'm thinking about it, my wife had an idea for our next class. I didn't have enough time to get ready for this time. But for my next class, I want to make things a little bit fun at the beginning. So I have 2 requests. Number one, I'm going to send you a little poll, and I want you to type in like the thing that you are most looking forward to when the shelter in place is lifted. I don't know, it's going to be hard for me to choose. I have many things. And then number two is I want you to bring, this is like no one shares their picture, but if you're willing to, I want you to bring a pet. So I'll see if I can capture one of my cats and just share a picture of something a little silly. So I'm going to share a picture of my cats. I have 2 cats. I'll see if I can find them, get them on camera. All right, so we have next question is number 11. So let's hop over here. Number 11. Oh, I was going to do this as an example of one like this. Okay. Oh, I clipped a little extra there. That's all right. Okay, so we are minimizing the cost to make a can. Cylindrical container, so let's draw a nice cylinder, has a capacity of 10 meters cubed. What is that really saying? Capacity of 10 cubic meters.
The volume is 10 cubic meters.
Yeah, that's a volume. That is a cylindrical, I said can. This is a container. This is a big container. 10 cubic meters is a lot. That's a meter, right? A meter by a meter by a meter. That's like off screen here. A meter by a meter. That's like, okay. Yeah, that's big. Okay, it's going to be produced. The top and the bottom are made of material that cost $20 per square meter. And then the side is a little cheaper. The side is $15 per square meter. Find the dimensions that will minimize the cost. All right, we want to minimize cost. Well, it looks like cost is going to be $15 times the area of the sides, plus $20 times the area of the top and bottom. We'll just call it T and B. It ran out of space. Okay. Let's see here. Cost equals $15. Area of the side, $20. Now, top and bottom are easy. Those are just circles. So they're each pi. I guess we need to label some stuff here, right? We should label the radius. Let me label it on the other side. And the height. So the top and bottom are just circles. They're pi r squared, but there are 2 of them. Right, top and the bottom. So area of the top and bottom is each pi r squared, but there are 2 of them. For the sides, I like to think about this. Imagine if you cut this and then unrolled it and folded it open. What shape would it make?
A rectangle.
Height. And then the other side is actually the circumference of the circle, because you've got this circle, right? And then you roll it open, and so you end up with the circumference, which is 2 pi r. So the surface area of a cylinder is actually 2 pi r h. It's just a rectangle. 2 pi r is the width, and then the height h. So cost is equal to 30 pi r h plus 40 pi r squared. And again, we have a problem here because we have cost as a function of 2 variables. This is a multivariable function. We actually did almost this identical problem in Calc 3, but they are able to handle multivariable functions. You are not, so we need to use another piece of information to get this down to a function of 1 variable, and that's where you have this volume. So somehow we're going to have to use the volume. Volume of a cylinder, any cylinder, not just circular cylinder, volume of a cylinder, we think of cylinders as they're all circles. But what a cylinder really is some kind of shape. Some kind of shape, and then parallel sides, and then I'm not going to be able to draw that same shape on the bottom. Right, that's a cylinder. A cylinder has the same shape on the top and bottom. We think of cylinders as circular cylinders, but those are special kinds of cylinders. They're the most common, but anything like this is cylinder. So the volume of that is the area of the base times the height. So for a circular cylinder, our volume will be the area of the base, pi r squared times height. And so now we need to do the same thing we did last time. Solve, we have 10 equals pi r squared h, and we need to solve for either r or h and substitute into the cost equation. I don't know about you, but I'd rather avoid square roots. And so I'm going to solve for h. H will be 10 over pi r squared, and we're going to substitute that in. So now I'm going to have cost as just a function of r, 30 pi r times 10 over pi r squared plus 40 pi r squared. And so then the cost becomes, looks like 300 pi over r, because we lost the squared, plus 40 pi r squared. Okay, so again, that's usually the biggest challenges. So what questions? Haley, do you have a question so far?
Yes. Should there be a pi with the 300?
Oh, you're right. Because, and I crossed it off and then I wrote it again. Everybody see that? Yep, good catch. Right, the 300, the pi's, there was a pi in the denominator too. Yep. Good. Was this your question, Haley, or was it like it's not trivial after this either? So.
No, it was just that. That was just my question.
Okay. Okay. Should we keep going? What do you think? Here, just do you see if you click on manage participants, there's a yes and no, like a green yes and a red no. Just check whether you want me to keep going or not. Okay, I see some yeses. Good enough for me. Okay. Whoa, lots of yeses. Okay. All right, let's keep going. So I'm going to rewrite this because I don't like taking derivatives like with a quotient rule, right? I would rewrite it 300 r to the negative 1 plus 40 pi r squared. And now we'll just use the power rule, negative 300 r to the negative second plus 80 pi r. And again, we're going to set that equal to 0, looking for critical numbers. I'm going to rewrite it now with negative exponents to solve. Maybe add the 300 over r squared to the other side. This is going to be an ugly number. Multiply by r cubed. Divide by 80 pi. And so r is the cube root of whatever that is. On a lot of these application problems, we actually do want a decimal approximation. I mean, not that this is the process for designing containers. It's usually more complex than this, but if you did do something like this, nobody's going to make a container and like go to the factory, say, okay guys, I need you to make a container that's cube root of 300 over 80 pi meters radius. Like nobody's going to do that. So it'd be nice to have a decimal approximation. Make it easier just to type here rather than using my phone calculator. My favorite calculator are decimals. They have a scientific one. And what was it? Cube root of 300. I mean, I guess we could do 30 over 8. That's fine. Pi. So about 1.06 meters. 1.06 meters. And then the height is supposed to be 10 over pi r squared. So that's 10 over pi times cube root of 300, or 30 over 8, I guess. We could do even better than that, right? That's fine. Okay, so that's 10 over pi times that squared. Sorry, squared. 10 over pi r squared. So 10 over, copy paste, pi times this squared. Wow, okay. I think that looks right. 10 over pi r squared, yeah? So about 2.83 meters for the height. So radius will be cube root of, and I guess we could do 30 over 8 or 15 over 4 pi. That's the radius. I think I simplified that correctly. 300 over 80, 30 over 8, 15 over 4, yeah. That's about 1.06 meters. And then the height, I'm sure we could simplify this. It is not worth my time or your time to simplify that. I'm sure you can simplify that to a cleaner form, but that's about 2.83 meters. So are we good on that one? Anybody have any additional questions on that one?
Professor Cade.
Yeah.
Examples shown by Dr. Sugar and in the notes in the book.
Uh-huh. Yeah.
With the domain, and then they find the absolute by showing a proof of it.
Uh-huh.
How would you do with this one?
Yeah, it's a good question. So, because really what we're trying to find is we kind of went a little quickly here and made some assumptions. Sometimes on these, the arguments that I will make is that logically, often you can know just logically that this has to be the maximum. But the point is well taken. I guess for this particular one, if you look at the domain for this, function, like what possible values are there? It's not quite as simple as finding an absolute, because the domain, you can see how you can't put in an r of 0. If you think about that, you can't have a radius of 0 because the height would need to be infinitely tall in order to still get the volume of 10 cubic meters. So you can't put in a radius of 0. And then as the radius increases, there's really no restriction on the radius. It can get infinitely large. Then the height correspondingly gets infinitely small. So the domain for this cost function is 0 to infinity. So you can't plug in endpoints because there are no endpoints. So to Christopher's point, what if we wanted to prove that this indeed gave us the maximum volume? Like, how do we know it's not a minimum? Maybe that's the smallest volume. How do we know that it's a maximum? Now, how could we prove that if we can't do the absolute? So what Christopher's saying is, if you get the domain for a function and it's limited to be between a and b, what you can do is just find the function at a, find the function at b, find the function at your critical point, and then whatever the biggest of those is, that's the maximum. Whatever the smallest of those is, that's the minimum. But our function does not have a closed domain. It can go all the way to 0, but not 0. So 0 is not possible anyway. And then there's no upper limit. So how would we prove that this is a maximum?
Could you plug those numbers into the volume equation that we wrote at the top, the pi r squared times h, and then see how close that is to the 10?
Well, it's going to give you the 10. It better. It better give you the 10 because that's how we solved it. So unless we made a mistake and we're rounding here, if we didn't round, it would be closer. But all that shows is that it gives you the volume of 10. It doesn't show that or not maximize, sorry. What are we trying to do again? I was saying maximum volume. I was answering the wrong question. What were we trying to optimize?
Minimize the cost.
Minimize the cost. So the question is not whether this is the maximum. So let me put below here, question, how do we know this minimizes the cost? Go ahead, Christopher.
Could you use the number line and have it from 0 and then to infinity? And it should go from negative to positive at that point, and that would show that it's a minimum.
Right. So we have our 1.06, and we're finding a number line for the derivative of the cost, and it hopefully should be declining up to 1.06 and then increasing again after the fact. To Haley's point, I'm trying to do this. I just did it on my phone, which was a mistake because you can't see that. But it is a good idea to double check. And without rounding here, this is 9.99. So it's good enough, right? Good enough, close enough to 10. So that confirms that the volume is 10 there, but it doesn't tell us that the cost is minimum. And Christopher's right. So if we try like 1 and 10 in our C prime function, C prime of 1, what was it? Negative 300 over R squared. Where did it go? Plus 80 pi times 1. Yeah, this is going to be negative because you have negative 300 and then 80 pi is like 3, so 240, so negative 300 plus 240-ish, 250, 260, something like that. So yeah, that's definitely going to be negative. And then at 10, it's definitely going to be positive because it's negative 300 over 10 squared, so that's only negative 3. And then you're going to add 80 times pi times 10. That's definitely positive. So if we had to prove that this was a minimum, that would be the way we could do it. The way that I would argue logically is, okay, so there's definitely a critical number there. As R gets closer to 0, then the height gets infinitely tall and the costs are going to explode. They'll get infinitely large too because the height gets infinitely large. And as the radius goes to infinity, well, then the radius is going to be infinitely large and you're going to have this infinitely large top and bottom. And so the costs are going to go to infinity there too. So either endpoint, kind of logically, the costs are going to explode. If we graph it, you'll see there's a vertical asymptote at 0. And then it kind of increases like a quadratic after that. Cost equals, what was it, 300 over R. And then plus, oh, I lost it already, 40 pi R squared. All right. This is a big, oh boy. We can't really see, where is it? It's way out because the costs are really big. We need to change our Y scale. I don't know if I'm going to be able to, because we need to change the X scale to be between like -1 and like 3. There we go, see? I knew I needed it really small because our radius was about 1 was the optimum. So you can see the cost explodes as the radius goes to 0, and then it increases after that and kind of steadily continues to increase. And then here's our point. There it is, look, 1.06. That's our minimum. So Desmos is kind of cool. If you click on it near the minimum, it'll actually find that minimum for you. Okay, good. That was a good one. That one was, I would say this one, just trying to give you a gauge of difficulty level for exams. I don't think we'd see one harder than this. I think usually test questions, I've had some that are simpler than this or this level. Just when you involve the pi in there, when you have rectangles or triangles, they're usually just easier to deal with. So this one's a little more challenging because of the pi involved in the answer. But this process is pretty much always the same. You make a function, you use the other fact, which is that, that volume fact. You use the other fact to make your function a function of one variable. And then once you have it to be a function of one variable, then you just take the derivative, set it equal to 0, and solve. All right, good questions on number 11. Any other questions on that one? Okay. Any other additional homework questions from, we're still working on 4.7 right now. We can move on to 4.8 in a little bit, but I thought let's stick with 4.7 for now. Haley asked about number 9 also.
Professor Kramer,
Yeah.
I have a question just for the setup of number 5. Would that one be where we set the values to the 200 meters, but for like the plots on the two sides, would we have 2x and then for the 3 lines be like 3y? Would that be the right way to kind of set that up to make sure that we're getting the largest area?
Yeah, let me take a look at that one and kind of start from scratch, and then we'll do Haley asked about number 9. We'll do that one next.
Thank you.
Okay, 200 meters available for and then divide into 2 plots. What is the largest area that can be? Yeah, so I think you're right. Let me go to red, nice and bright here. So did you use X for the horizontal? Brittany?
Sorry, I muted myself. X, yes.
Yep. So that sounds good. So I think we do X and Y. We want to find the maximum area. So again, area will be X and Y. You can use length and width or whatever you want. And then we have the amount of fencing. And to Brittany's point, it's a little more interesting this time. We have amount of fencing is 200 meters, but it's 2X because there's the bottom and the top, but then 3Y. Yeah, you are correct. Yep, so it's not like the previous one, number 3, whatever that we did, where it's just the perimeter, but there's 3 Ys. You have 1, 2, 3 Ys, because there's that fence in the middle too.
Okay, perfect. Thank you. I just wanted to make sure I was starting it off right before I got myself confused. So thank you.
Yep. All right, and let's take a look at number 9. Oops, sorry. Go back over here. Take a look at number 9, minimum surface area. There we go, minimizing the surface area of a box. Oops, moved the wrong one. There we go. Minimizing the surface area of a box. Let's see, we have an open box with a square base. Let's draw a box. Square base. So I'm going to call it X by X by Y, and it's open top, so I can actually draw the back there. It's kind of cool, it adds some dimension, so there's no top to it. It has a volume of 2,000 cubic centimeters. What should the dimensions of the box be if the amount of material used is to be a minimum? We want to minimize the amount of material. Well, if we're minimizing the amount of material, what are we really minimizing?
The volume of the box, or the capacity the box would hold?
That's 200 cubic centimeters. So that's a set number. Yep.
The surface area?
You are correct. The surface area. The surface area. Okay, so we have the bottom is x squared, and then we have 4 sides, and they're all xy. Do you feel the rhythm of these now? Do you know what we're going to do next? I mean, I'm not saying you, Haley. I'm just saying anyone. How about somebody who hasn't answered yet? Do you know what we need to do next?
I have a quick question.
Yes.
Where did you get the 4xy and the x squared from?
Well, there's a bottom down here. At the bottom.
Mhm.
That's the x squared. And then the sides are x times y, but they're all x times y. All of these heights are all y. So each side is x times y. They're all x times y.
Okay, thank you.
So my question again is, I have area. It's a function of x and y now. And we're trying to minimize the amount of material, aka minimizing that surface area. What do we need to do next? I'd love to hear from somebody who has an
All
answer.
per single variable.
That's right, Chantel. We need to get it in terms of a single variable, and that's where we'll use our other fact, the volume. Volume is x squared times y. And I guess, again, I don't want to have square roots, so I'll just solve for y. Y will be equal to 2,000 over x squared. And so now I'm going to have area, call it capital A. Now it's going to be a function just of x. X squared plus 4x times 2,000 over x squared. And now I am already x squared plus 8,000 over x. And how about let's just ask this, what is next?
Solve for 0.
You're close. You're close. You're one step ahead.
Oh.
Yeah, you got it though.
Get the derivative.
Right. So Christopher,
Oh, yeah.
so yeah, Tvante, you're looking for critical numbers first. So yep, you're close. So we want to find a prime and then set that equal to 0. If we set a equal to 0, it'll just say, well, that's kind of weird. I don't think it's possible. I think you'll get a negative number. It's not possible to have a 0 surface area. You would see that. You'd get an answer. You'd be like, wait a minute, this can't be right. So yeah, so next you take the derivative and set it equal to 0. And I think that should be pretty straightforward. I think you can all do that. All right, Haley, we good on that one?
Yes, thank you.
All right, we're doing lots of great examples. Let's talk a little bit about 4.8. We can do some additional 4.7 optimization examples if you wish, but I want to talk a little bit about 4.8. I do have some examples we can do, or I will take some homework questions there as well. A reminder of the schedule. We're going to talk about questions today from these 2 sections. Thursday is going to be exam review. We'll do some questions if you have them. And then I have to put that on my list. I have to post, make an exam review. I'll work on that today. In fact, I can work on that right after class. Oh, shoot, I forgot. I never went over your quiz. Oh, let's do that now. You should see, if you are interested, there should be solutions posted under Unit 4. I have the original here, so I'm just going to go there. Where is it? Quizzes. There it is.
Wait, when's the test?
Thursday after class, and then I think it'll be, did I say due Friday, I think? So I don't think, yeah. We talked about it. So we're going to meet on Thursday and do a review in class and answer homework questions, whatever. And then I'll post the exam after class, and then it'll be due by the end of the day on Friday.
Oh, okay.
Yep, that'll cover chapter 4, except the 2 sections we skipped.
And when do we go back to class?
We do not.
Oh, we don't.
I know. Yeah, it's
Okay.
they decided the campus might be open again tentatively it's like May 4th or something. But our class and most of your classes will not be going back to campus. The only ones that might be classes that have labs with them. Oh, Lorenzo, I see your hand, so I'll come to you. So, and then those might actually extend into the summer if you have like an anatomy class or something.
Oh, wow.
Yeah, yeah, it's a little crazy. And then summer classes, only classes that were online before are going to be taught on this summer, and they were staying for online this summer too.
Okay.
Yeah, it's wild. And then Devontae, did you get the notice about the grading changes too?
I did not.
Yeah, it's okay. It's okay. Maybe I'll just quick refresher for everybody. So I'm going to turn in grades like normal. However, you can all the way up to the last day of the semester, you can decide, you know what, not for this class. I think everybody's going to be fine for this class. But if you're really struggling in another class, you can withdraw all the way up to May 13th.
Oh,
Usually,
wow.
yeah, they're being really flexible with that because obviously crazy times.
Mhm.
And then second, for your grades, if you decide, you know what, man, I'm getting a C here and I really know I could have done better, you can change that if it's okay for your degree to just credit. It counts for your degree and doesn't affect your GPA. You have to be careful though. You have to meet with an advisor to do that. And for Calc especially, if you're going to take Calc 2 somewhere else, like that might not count. So you got to be really careful. You might need the C. You might need the C in order for it to count. But you actually have until June 4th to decide that.
Oh, wow.
Yeah, it's cool. Yep. So that's even after the semester is over, there'll be more emails out.
Awesome. So either way you pass.
Right. Yeah, if you get a C or better, you can decide, you know what? If you get an A, everybody will just keep the A, probably a B also. But if you were like doing okay, and then like, you know, the all trying to learn in this format suddenly made your grade drop, you could decide, you know what? I'm just going to take the credit and not the grade.
Okay.
And there are no Fs. Every F will be changed to a no credit. And then a D, you can choose. Do you want to take the no credit or do you want to take the D? So yeah, super flexible. Yep. Yeah, and we are not going back. Not going back at all, which makes me sad. Like I'm trying not to think about it actually. Yeah. Lorenzo, you were going to ask something too?
Yeah, never mind. That you already got it.
Okay. All right, man. All right. So the quiz, let me talk about the quiz. I'm sorry I skipped this. I was going to do this at the beginning of class. I am just like on like quarantine brain lately. So for the first one, you're looking for finding the critical numbers and the first derivative test. People did pretty well on this one. It's just a polynomial. You can factor out a 3. So the only 0 there, the only critical number is -2. When you do a first derivative chart, they're both positive. So there actually are no relative extremes. For number 2, this one was hard and honestly harder than I thought it was going to be. So I was pretty liberal on my grading here. The first derivative is okay, but like setting them equal to 0 and then the second derivative, this was not trivial. So if you got this one, that's awesome. So mainly I was looking for a process here and I gave lots of points if you knew the process. Some people got stuck on the second derivative and then wrote the process, which is awesome. Do that on tests as well. If you get stuck, right? Well, here's the process. So you know the process. So first derivative, it's just exponents, which is fine, but then they're fraction exponents and they're negative fraction exponents. So the way that I did it is I took the derivative. Let me switch to a red pen so I can highlight things again here. Maybe I can switch to a highlighter. So I took the derivative with the power rule, and then I switched to writing it as a reciprocal in order to solve it. And then you can see for the rest of it, I got a common denominator and combined them together. I like a single fraction because if I'm setting it equal to 0, then the numerator is equal to 0. If I'm seeing where it doesn't exist, it's the denominator equal to 0. So that's how I got the 1/8 and the 0. Those are the two critical numbers. And testing, I've got some numbers that I tested here. It's there's a relative max. Geez. Relative minimum at x equal 1/8. You can see the decreasing up to it and then increasing after. And then the second derivative, here's where some people got thrown off. They had this nice simplified second derivative and then tried to use the quotient rule. I would actually go back and use the one with the exponents to do the second derivative. It's always easier to take derivatives when they're just exponents. So that's what I did, is I basically repeated this whole process, but with the second derivative. So you'll see I have the powers here. Again, for the second derivative, again, rewrote it with the exponents now in the denominator, and then I got a common denominator so I could combine them together, and I got one fraction at the end, and again set it equal to 0, see where it doesn't exist, and find the concavity and the inflection points. So that one was pretty hard, just the algebra. The algebra was pretty hard on that one. That one was not a good quiz question. I wanted to do some that wasn't just a polynomial, and I should have worked it out ahead of time. So I was trying to be generous with the grading on that one. It was pretty challenging. And then the third one, this was another one where I like the question, but I should have done it first because I think there were a few people who got letter B correct, but not because they knew what they were doing. Here's the key on this one. For letter A, where's the function increasing? Well, it's increasing when the derivative is above 0. Well, the derivative is above 0 here. This is where the derivative is above 0. So it's only from 1 to infinity. For letter B, where is it concave up? A lot of people looked at that and said, oh, it's a parabola. It's always concave up. Well, yeah, it's always concave up, but not because of why you thought. It's concave up when the second derivative is above 0, but the second derivative is almost always above 0. If you made a second derivative chart, it's 0 when x is 0. It's positive before, positive after. And so it's concave up and then continues to be concave up. And so it's concave up for the entire region. This one is a little confusing about whether or not to include 0. Your textbook doesn't really answer that well, so I accepted either version, whether you included 0 or not. It's just technically, what does it mean to be concave up? What does that definition mean? And it's not worth us stressing out about it. So if you left 0 out, it's fine. But technically, if it's concave up before, concave up after, we can say it's concave up on the entire interval. So the key here is the graphs that we were given, they were the graphs of the first and second derivatives. So you have to look at where are they above 0 if you're looking for increasing, or where is the second derivative positive for knowing where it's concave up. All right, does anyone have any questions about the quiz? Are you getting the feedback okay in D2L? Like, can you read the comments that I write on your quizzes in D2L? All right, Sandra said yes, okay. Good, you should be able to open up the Dropbox and then see, I do like pink in there because it's easy to read, easier for you to read and see, pink or purple, whatever. Okay, all right, so I think, excellent, that is it for the quiz. So let's go back to homework. We were trying to answer questions. We were going to switch to 4.8. So did anyone have any questions? Where's my 4.8? I couldn't get this in the ebook, so I have it in a PDF form. Did anybody have any 4.8 homework questions? 61 and 25. Let me go in order there. We do 25 first. So what we're doing here in this section is instead of taking a function and finding its derivative and answering all these questions about that, what we're doing here, we should read the directions, is we're going to find the antiderivative of each function. So what that means is that we're going to treat this, treat this as a derivative. And then work backwards. Now, if you were to look at that right now, you're like, dude, that's a quotient. Does that come from a quotient rule and I'm supposed to reverse quotient rule it? No. There is a better plan for this. The better plan for this is to use some algebra and rewrite it and divide each of the terms by x. And then personally, what I would do is I would then simplify and write them with exponents. So this would be x to the negative 1/2, and then 4x to the negative 1. And so then now we're going to work backwards and think to ourselves, what kind of reversing all the derivative rules. And I'm not sure what kind of work is we are showing here. So I think we're doing like capital F. Does that sound right? For the antiderivative. There's different notations here. And
that's what the book used was the capital F.
Okay. All right. Yeah. Thank you. We'll try to be consistent with them. So antiderivative. Okay. So we have to think of the derivative of what function. I'm going to just carry the 3 along with it here. The derivative of what function would give me x to the negative 1/2? Well, it's a power. And so I would have had to subtract 1 to get the negative 1/2, right? So if I'm working backwards, what is that? What must that exponent have started at?
Positive 1/2.
Right, positive 1/2. Lorenzo is correct. Positive 1/2. So you're basically thinking of your derivative rules you subtracted. So here you're going to add. Now I have a problem. If I take the derivative of that function as written, it would be 1/2 x to the negative 1/2. But I don't have the 1/2. So I need to modify it a little bit. What else do I need to kind of include in there?
Multiply it by 2.
By 2, yeah. Now let me see here. I was having a hard time. See, this was frustrating. I could not get the ebook to load for that whole section. I was trying to decide, because I haven't taught in this book before. So the last time I taught this class was like a couple years ago, a year and a half ago. And there was a different text. And so I was trying to download and like, well, what notation does your book use? What examples do they have? So I'm scrolling through here and then it just kind of ends on me. Okay, so here's the one we're going to use. Whoa, go back to that table. I'm going to snag this table. And paste that in here. We can use this table too. All right, so we can use this table. The one we're doing right now is the power rule. So you can also think of x to the negative 1/2 plus 1 over negative 1/2 plus 1, which would be x to the 1/2 over 1/2, which is, as Lorenzo already noted, 2x to the 1/2. So the antiderivative of x to the negative 1/2 is 2x to the 1/2. I'm going to work all the way through this one. I want you to be patient if you're a little bit lost, because I want to show you some great tools here. The beauty about these problems is they're really easy to check, which is really nice. Okay, then we have 4, and then I have to figure out the x to the negative 1. You can see it on the table, but this again, if you remember your derivatives, what function's derivative is 1 over x?
Natural log.
Well, natural.
The natural log, yep, right, Savante, right, Christopher. So this is actually natural log now. This absolute value of x is important. I'm going to put a plus c here because there's some constant there that could have been there. The absolute value is important. I would encourage you to look at your, where are the notes? What section was that in? We had an important discussion about the natural log and the absolute value and all that. Oh, I am not going to remember where it is, so I'm just going to flip through until I see it. This is not an effective plan. Where are the log functions? They're in, I saw exponential. Logarithmic functions, yay. Okay, page 68. Page 68. And of course, I don't have, I can just like show you on the screen. No, it's just showing white. Stop. Can you see? So we took the derivative of the natural log of the absolute value of x, and we got 1 over x. And so what that says is when I have 1 over x as the derivative, that it must have started with the natural log of the absolute value of x. That was not an effective way to show you the notes, but that's what I've got. So page 68, if you want to look at why that's the absolute value, it's important. So my antiderivative then is 6x to the 1/2 minus 4 times the natural log of absolute value of x plus c. So here's what I wanted to show you. How do you know as a student, you have these problems on the test. You'll have a couple of them on the test from 4.8. How do you know whether your answer is right? How do you check your work?
You can take the derivative of capital F and make sure it's the same as lowercase f.
That's correct. Is capital F prime equal to the lowercase f? That's the check. So let's do that. F prime of x, capital F prime. Let's see, 6 times 1/2 would be 3x, and then we subtract 1, so negative 1/2 minus 4. We just showed on page 68, the derivative of the natural log of the absolute value of x is 1 over x. And the derivative of c is 0, and we got our original function, right? That's it. That worked. It worked.
I've got a question.
Yes.
So I know we can technically work backwards based off of what we've done so far in the semester, but for the exam, are we going to get this table? Because I was kind of referencing it a lot in my homework, making it easier and not taking so much time to try and work it backwards.
So what is your, this is a bigger question. What is your plan for next semester? Are you taking Calc 2?
For me personally, no.
Okay. So for those that are moving on, especially, you can't be referencing a table on these. These have to all be mentally memorized. It's like the derivative formulas, right? So I would say when we get to chapter 5 and we're doing this concept called an integral, we need to know these. However, I think that it will just happen. Right now it seems overwhelming because we're doing all of them at once. So here's what I would say. When we get to this test, we're not going to have all of these on this test. We're not. It's too much. So we are going to focus on the simpler ones. the trig here, the trig, and I guess I could have included everything on the left. The trig, polynomials, log functions, exponential functions, trig functions. Just those. We're not going to talk about inverse trig functions, and then you don't even know what this last category is. We haven't talked about it. So the majority of them will be polynomials, exponential functions, and then trig functions. And so what I do on a lot of these is I just like almost like take the derivative preemptively. Like, well, if I want to end up with cosine, let's see, what's the derivative of sine? The derivative of sine is cosine. So I do think that you need to have these memorized, but we're going to focus on simpler ones for now. So don't worry about the inverse trig functions for now. Those actually probably will be more of a focus in Calc 2 than they would be here, so you don't have to stress about those at all. So I do think you want to have these memorized as soon as possible. For the next test, the problem is with the formula sheet, like if you have this on a formula sheet, then well, there's nothing to do on the next test. You just look on your formula sheet and answer the question, you know? So it's hard to know how to handle that. Yeah. So I would say my goal would be for you to have at least the ones that are boxed in there, have those memorized. Any other questions on this first example here, this homework question 25? All right, I think we have time for one more. We'll see, and I can hang out after if you have to go. If you have to go, it's already 10:34, so feel free to go, but I'm gonna try to answer Sandra's and Haley's homework questions. So you can hang around if you would like. 4.831 was next. If you do need to take off, keep your eye on D2L for an exam review packet. I'll post that soon. All right, so Sandra asked about 31. Boy, that one is all about recognition. We need to look over at the table here, and you will see that one over here. Let me factor the 7 out.
Oh, yes, I see now.
Yeah, it's all recognition. It's all recognition. So that's, again, it's just practice. So don't feel bad. Yeah,
and
don't
also
feel bad.
have a question about the tangent, like, the arctangent. Do we need to memorize those ones too?
Not for this test. No.
Okay. But even future on, like,
I don't think so.
So do we need
No.
to? Okay.
No. Those will be ones that, like, especially arctangent and arcsine, you use those a lot. You'll almost memorize them accidentally, but those will be ones that even I tell my Calc 2 students, we usually have them on a formula sheet, and you don't have to memorize them all.
Okay, I get it now.
Okay, all right, good. And then 61, everybody see that, by the way? Do you see the arctangent? So that one would be the inverse tangent, 7 times the inverse tangent. And then 61, Haley had asked about. Let's go, oops, wrong PDF, not that one, this one. 61, ooh, these are getting harder. Oh boy. Okay. Need more space here, a lot more. BMW 6 Series can accelerate from 0 to 60 miles per hour in 5 seconds. If the acceleration is constant, how far does the car travel during this time? Well, here's the key for this one. I'm going to make some notation here. Hopefully you'll recognize this. I'm going to let S of t represent the car's position or displacement. And then V of t, which is velocity, which is S prime of t. That'll be velocity. That can be positive or negative. You can work backwards. And then a of t, which will be s double prime or v prime. Let me do it in this order. V prime of t, s double prime of t. That will be acceleration. So what we're going to do here is we're going to start with acceleration and then try to work backwards to get the position, to get an equation for the position. Okay, the key here is the acceleration is constant. So the acceleration constant means that the acceleration can just be the change in velocity over change in time. We need to choose some units here. I mean, speeds is miles per hour, but I don't feel like I want to get distance in miles. How far is the car going to travel? Because it's got to be a fraction of a mile in 5 seconds, right? 0 to 60, 5 seconds. Plus the 5 is in seconds. So I think what I want to do is do everything in maybe feet and second. Is that okay? Feet and seconds. So 0 miles per hour is obviously equivalent to 0 feet per second. But 60 miles per hour, 60 miles per 1 hour, let's see, would be 3,600 seconds in 1 hour. You can do this conversion in Google if you want to too, but it's good for us to know what they're doing. And then 1 mile is 5,280 feet. So that will give me feet per second. So let me do that quickly here. Okay, 60 times 5,280, oops, divided by 3,600. Oh, that's convenient. 88 feet per second. Okay. So acceleration is the rate of change of velocity. How fast is the velocity changing? And ours is just constant. So we can just do an algebra problem here, no calculus. Just say, well, it ended at 88 feet per second. Subtract the 0 feet per second. That's the change over 5 seconds. So it'll be 88 fifths, and it's feet per second per second. It's kind of a weird unit. Most people will see feet per second squared, but I like to think of it as change in velocity. What is 88 fifths? Let's get a decimal there. 17.6. 17.6 feet per second per second. That's acceleration, rate of change of velocity. So going back to our process up here, acceleration is constant, 17.6. So let's work backwards. Acceleration is the derivative of velocity. So velocity is the antiderivative of the acceleration, working backwards. So what function would give you a derivative of 17.6?
$17.6
Times t, yeah. And technically there could be some constant, right? Because the derivative of the constant would be 0. The only way to know that constant is to know something about the velocity. If I had the velocity at a specific time, I could figure out the c. But in fact, I do have the velocity at a specific time. I have it at 2 times, in fact. Go ahead, Brittany.
They said at 0 and at 5 seconds.
Right? We know the velocity at 0 is 0, and the velocity at 5 seconds is 88 feet per second. So I would just use the velocity at 0. Velocity at 0 is 0, implies, let's see, 17.6 times 0 plus c equals 0, and so c is 0. So velocity is 17.6 t. And think about the units here, by the way. Remember, it's feet per second. And so you multiply by t, and your velocity increases every second. So you're multiplying by seconds and you're getting feet per second. So that feet per second makes sense here. Or, I mean, I don't know if it makes sense to you. It makes sense to me. Okay, and then we're going to repeat this. Now we're going to say, well, the position would be the antiderivative of velocity. Velocity is the rate of change of position. So position will be the antiderivative of velocity. We know it has to be a t squared because the derivative would give you a t. How do I figure out the constant?
Wait, what are you asking?
Well, I'm doing the antiderivative, and we know the antiderivative of a t must be a t squared because the derivative of a t squared would be 2t.
Divided by 2.
Divided by 2, Lorenzo's right. Yeah, when you take the derivative, you multiply by 2. When you do the antiderivative, you divide by 2. And that was in that formula sheet, by the way. That was if f of x is, I think they called it x to the a, the antiderivative would be x to the a plus 1 over a plus 1. It's like the power rule. And again, we need a position, but if you're going from 0 to 60, well, initially you just start at the beginning. So s of 0 is 0, and so that means that this c is also 0. And what is 17.6 divided by 2? 8.8? Yeah, 8.8 t squared. So that's the position or displacement at time t. And we're looking for how far does it travel in that 5 seconds. So in that 5 seconds that it's flooring it from 0 to 60 miles per hour, how far does it actually travel? So the distance traveled in 5 seconds, how would we find that?
Just substitute 5 in for t.
That's it, s of 5. 8, it looks like 5 of 5, that's an s. S of 5, 8.8 times 5 squared times 25, so 220 feet. All right, we good with that one, Haley?
Yes.
Okay. All right, I'm going to end the class, but I am available. In fact, I could do another Zoom meeting with you personally if you have homework questions. I said I'm going to be available until noon today on Tuesdays. So just shoot me an email if you have additional questions. Otherwise, we're going to end this class, and I'll see you on Thursday, and we'll do some exam review.